Very good. So the next family of methods we will see are these trust region methods. And these are used uh, in cases, here you have, for instance, non-linear ill-conditioned or non-convex problems. And also I would add, when the goal function you are trying to optimize is very expensive. So let's say that this one is the landscape of the goal function you want to optimize. You start here, and then the problem with the evaluation of this function is that it is non-linear, it is unconditional, it is non-convex, or it is very expensive. So let's say that evaluating the function takes, I don't know, 10 seconds, while evaluating a small model that approximates the function is just milliseconds. So what you do is you start from your initial point, you construct a model around it, so kind of parabola around. So you construct a quadratic function, and then you evaluate the quadratic function as many times as you like. And that is very cheap. You can converge to the local minimum of the model, and then go back to the original goal function to see if you have really improved. If it was a good model, then you would have improved. If it was not a good model, then probably your evaluation of the underlying function will be worse, and then you will update your model somehow with the new measurement. So as the algorithm progresses, the region in which you trust your function is increased or decreased depending on whether you're doing good updates or not. So if you succeed in your updates, then you increase the region in which you trust your model. So the parabola, you think it is a good approximation in a larger region. And if you are making worse approximations, then you decrease the region in which you trust your model. That is why it is called the trust region method. So they work like this. So let's say that you have a local model at iteration k, and this S is centered at the middle of the trust region method. So for every trust region area, S equals 0 is the middle of the area. So it is kind of displacement with respect to the current position. And yeah, so you are around xk. This model is supposed to be approximating this one. And you trust this model in a region defined by a radius delta k around xk. So instead of evaluating or trying to minimize f of x, that is a complicated function, you minimize your model subject to the displacement with respect to the current point has to be smaller than the trust region area. And once you find the best displacement with respect to the current position, you simply add it, you have a new point, and then you evaluate the underlying function at this new point. And if it is better, then you accept the step. And if it is, and then independently of whether it is better or worse, you have to take a decision on what to do with the trust region method. So you should enlarge it, you should keep it as it is, or you should make it smaller. And we will see a little bit more in the next slide about this idea. And the model that you can construct is typically it is a kind of quadratic function. So you have the current value at xk that you have because you have evaluated here. And then you have to estimate somehow the gradient or know the gradient analytically and construct an approximation or have the Hessian of the function. So you construct typically a quadratic function around that area, and then you minimize that quadratic function subject to this constraint. So this is a very easy problem. And then once you have solved what is the best displacement, you update your current solution. Okay, so yeah, this is the what we have just said. So now, how should I update the trust region area? So you will compute a ratio. So this ratio is how much the function has changed with respect how much the model has changed. Okay, so if the function changes in the same amount as the model, so the ratio is 1, then the model is a good model. So, and then if the model is a good model, so you increase your trust region area. So if it is larger than some threshold, here we are putting 0.75, but it can be relatively large number, large in terms of 0 to 1. So then you increase your trust region area because the function has decreased more or less the same amount as the model. Let's say that the function changes, but much less than your model. So then that means that your model is inaccurate. So let's say that this ratio is below 0.25, and then what you do is you reduce your trust region area. And if it is in between 0.25 or 0.75, you don't touch the region area. Is it clear? Yeah. Very good. Then we move on to a different topic, that is regularization. So we have been focusing mostly on minimizing some function, but sometimes this function is imposed, so it is ill-conditioned, or it is not convex, or it has some nasty properties that you want to avoid. Or on the other side, you might, so you might have some a priori knowledge about the nature of the solutions that you are looking for. So there are two reasons for adding regularization. So either to prevent bad behavior of F, so these clean-fold problems, for instance, or for instance, in machine learning, you want to prevent repeating because you know that the kind of solutions that you are looking for, they should have very or not high values. So the X should not take large values, but should be mostly 0 except for a few points. Or numerically, your algorithms are not converging well, and then by adding a regularization, you make it better behaved, or to incorporate a priori knowledge, like the ones I have said. Sparsity, that means most of the components of X are 0 except a few ones, or smoothness, so the values of X should change slowly. And then by adding this regularizer, what you are doing is changing the landscape. So on top of the landscape, so on top of the shape of F, you are adding something, and that is changing the geometry, the curvature, and all that. And so in general, they converge faster. In machine learning, they help to generalize because otherwise you are probably overfitting the training data. And here you have the typical representation of overfitting for both classification and regression problems. So in regression, it is, let's say that you're given a set of points and you want to find a model that explains these points. So a linear model, for instance, what we are changing here is the number of parameters of your model. So the more parameters you have, the more freedom you have to adapt to the points. If you have very few parameters, so a line just have 2 parameters that you can control. So it is not a very bad model, but it is not good either. So you see that there are regions that are very badly represented. For instance, if you put a polynomial of degree 2, now you are doing much better work. If you put a polynomial of degree 20, you can have a very low training error because you are going very close to the training point, but probably this is not the underlying function. So you are adapting to the noise. So how do you prevent that? And the answer is through regularization. So the regularizer will penalize having too many parameters with values that are significantly different from zero. And the same applies in classification. If you have to separate these sets of points, a very simple boundary will not do a very good job. Probably this is better, and this is just adapting too much to the training data. So what kind of regularizers do we have? So this one is one of the most common, these two actually are the two most common ones. So one is based on the norm, Euclidean norm of the vector x. So it is just the sum of all the components squared. And then it penalizes large values in the solution vector. So if one of the xi's is very large, this term will be very large, and because you are minimizing, with this penalization, this lambda is something relatively difficult to choose. We will see some technique, but in practice, still it is difficult or very expensive as we will see. So, because you are trying to minimize, and this is always a positive number, so you will try to make it smaller. So all the xi's should be relatively small. And the other one is this one that is almost the same, but instead of having squares, you have absolute values. And both try to make that the components are small. This one promotes that they are exactly zero. So many of the xi's will go to zero, and only the few that are really needed will be different from zero. And this is also used in this variable selection when you are doing regression, and you try to figure out which are the features that you should use to make the regression. So you can make this lasso regularization or compression, that is a particular technique of signal processing. Okay, and more names. This is also called bridge regularization or Tikhonov regularization. And here is a mixture between the two. So here you have the elastic net. The elastic net is a mixture between L1 norm and L2 norm. And then they are combined linearly through a parameter alpha. And another one is this total variation. So if your vector has an interpretation of a signal, for instance, so then they can compute the difference between one sample and the next, and then these changes have to be small, and this is called total variation. Actually, this one here is a kind of derivative. So the total variation actually is the L1 norm of the derivative. Very good. Then more common regularizers, so entropy regularization. So is this one that tends to make the distributions to be more uniform, or nuclear norm. So when you are dealing with matrices, you can compute the singular values of your matrix and then sum the singular values. The singular values are always larger or equal to zero. So, for instance, this kind of regularizations in matrix completion. Do you know the matrix completion problem? No? Okay, this is very nice problem. So let's look for some nice picture of it. So it is this one. So for instance, here, let's say that a number of people have to rate some movies, for instance, and then person one has rated movie 1 and 2 and 4, but not 3 and 5. person 2 has rated movie 1 and 3 and 5, but not 2 and 4 and so on. And the point is, can I take all the information from everyone to try, for instance, person 1 likes this movie and person 5 also likes this movie, and person 1 has not rated, which one? Number 3, but the 5th person has rated number 3. So I can try kind of take the information from person 5 to fill the information from person 1. Okay, so this is the matrix completion problem. So here it is illustrated with movies, but it can be measurements or whatever. So when you are so your final, what you are trying to minimize is something related to a matrix, and then something related to a matrix. So something related to a matrix, it makes sense that the regularizers have to do with something related from that matrix, and singular values is something that somehow describe very well the structure of the matrix. And for instance, in recommender systems, they are very much used. Okay, so here we have an example. So standard regression. So in regression, you have a linear regression. Your problem is of the form AX equal B. So you try to find the X that minimizes the error between your predictions and your predictions. And then you impose some properties on X. X are the parameters of your regression. Okay? So X is not. So X are your unknowns. They are not the observations. So if you have Y, you have some points, let's say, and you put a quadratic model here. So you say Y, my predicted Y will be beta 0 plus beta 1 xi plus beta 2 x I squared. So this is a linear problem. You can also write this as 1 xi squared. Then we have the vector beta 0, beta 1, beta 2. And this one here. If you put, if you collect all your measurements, and can have 1 x squared, 1 x2 x2 squared. So you can put this one as a vector y, that is some matrix x times a vector beta. But in general, this also has the form b equals nx. Okay, so in the slides we are talking about this formulation that is the same as this one, but maybe in regression you are more used to this notation. Okay, but in general, it is a linear problem in which you have observations, you have some parameters, we have a matrix that transforms your parameters into observations. Okay, so we are talking about regression, and these are the parameters. So it is a restriction on the parameters of the regression. And for this particular problem, there exists a closed form solution, that is this one. So it is something related to the system matrix and the regularization. And you can see that the eigenvalues of these, if lambda is very large, it is dominated by this term. So when you compute the inverse of that, that will be very stable. So that is what is said here. So it improves the conditioning of this matrix by adding some eigenvalues, by dominating their eigenvalues if lambda is very large. And lasso regression is like this one, but it's the L2 norm. It is the L1 norm. And now there is no closed form solution, and you can solve with any one of the methods that we have seen, these proximal methods, coordinate descent. Yeah. So at the end, this one will tend to make many of the components zero, except a few ones. This one doesn't promote that property, so it promotes that the x take small values, but they don't force them to be zero. So how do you choose that? So this is one of the most difficult parts. So here is it is a good method, this one. The problem with this one is that it is expensive. So if you set lambda equals 0, there is no regularization. So that this term doesn't appear. If you make lambda very large, this term dominates this one, so the data doesn't have any influence on your solution. You're mostly focused on having a small node. And then there must be a balance between the two. And then, for instance, this approach using cross-validation, it is very, it's very useful, no? So you cross-validation, you know, right? Okay, so you have all your data, you divide it into blocks, into subsets, and then, so K equal subsets. You take K minus 1, you estimate your model on this K minus 1 parts of your training set, and then you compute the validation error on the block that has been left out. And yeah, and then you repeat that for every block, for every fold, and you compute the average of the validation errors. That for a particular lambda. And this, now you repeat for multiple lambdas, and you choose the one that minimizes the average validation error. If you want this part, it's also a minimization problem in itself. So you can think of it as minimization with respect to lambda of the validation error. Let's call it error validation. That is a function of lambda. So it is a minimization problem. And again, you know a lot of tools to do minimization. So here it is explained as a simple exploration, but you could approach it as a minimization problem and use any one of the techniques we already know. But you see that the problem of this is that it is expensive. So for every lambda, you have to make 10 models. So let's say K is equal 10. So you have to construct 10 models for each lambda and twice every lambda. So that is expensive. Okay. And that is also a very nice interpretation of the regularization as a maximum a posteriori problem. So this is coming from Bayesian statistics. So let's say that in your X and Y, so X and Y space, X is your parameters. Okay, so in the problem regression these are beta, and Y is the set of observations. So it is in this plot that I did before. This one, it is X and Y together. So it is Y in the slide. So Y in the slide is the X, I, Y. So this is the vector formed by the two components. So you have some observations and data Y, you have some parameters X, that in the regression it was the betas. And then you have a likelihood function that given these betas, what is the likelihood of observing Y, of observing this deep data. And then you have some prior on the distribution of the parameters. And then you can compute the posterior distribution of X in Y. So what is the probability of having these parameters given these observations? And by the Bayesian rule, it is this one. And then we want to maximize this probability. So maximizing that probability is the same as maximizing this numerator, because the denominator does not depend on X. So there is nothing to optimize there. So it is optimizing with respect to X. So it is maximizing this one. And then you can take the logarithm of this, because you know that the logarithm is a monotonic function, and then maximizing something is the same as maximizing the logarithm of that something. So it would be the minimization with respect to X of this, the logarithm of this probability minus the logarithm of this probability. This would be F. This would be the regularization. Okay, so there is a very nice connection between regularizations and Bayesian approaches to data analysis. So the regularizer is some prior that you have from the distribution of X. So this is what is said here. So actually the loss functions that you normally use, they are also some, they also imply some prior, not some prior, but some assumption about the distribution of the observations given the X. So actually one, the most typical loss function is the quadratic one. So this one here. So this one is associated to a Gaussian noise. So you assume that the noise in your V observations is Gaussian, and then the logarithm of the Gaussian function. The Gaussian function is the square node. Actually, this is what is shown here. So let's say that your observations Y is some matrix times X plus some noise. The noise is a Gaussian, multivariate Gaussian distribution with this distribution. You have some prior on the distribution of the X, and then the logarithm of the probability of Y given X will give rise to this thing. So you recognize here the L2 norm, and the prior, that is this one. So it will come to this one. Okay, and then the maximum a posteriori, these are scalar factors, so scalar factors in minimization. Again, you don't care about those. And then it is this one. Lambda is combining the two. Any question? Okay, and then lasso. What about lasso? So lasso was this L1 node. So L1 node, you can do the opposite reasoning. So there must be a function. There must be a prior on the X such that the regularization is this one. So the regularization, that is this one here, has to be the minus logarithm of px. So what is px? So you simply solve here. So px is the exponential of minus alpha del 1 node. So this one. So that is called the Laplace prior. This is the Laplace distribution. So the lasso regression is related to this distribution, and the difference between the Laplace and the Gaussian distributions is in the shape of the tails. So the Gaussian is like this, and the Laplacian is something like this. Okay, good. So then we move on to another topic, somehow related. So we have used the L1 regularization to promote having zero components. So the vector should have a lot of zeros and a few ones that are different from zero. Why don't we explicitly say that? So why don't we say, I want to minimize this function subject to the constraint that the number of elements different from zero is smaller or equal to k. So this L0 known, sorry, let's put it like this. So the L0 known is the number of components such is the cardinal of xi different from zero. Okay, so this is a set, and then it is the cardinal of that set. So it simply have to count how many components are different from zero. Okay, so we want to minimize this with only using k components of x. And if we put it as a regularization, would be this goal function, and that is called a sparse optimization. So L1 promotes sparsity, but here the sparsity is explicitly stated. So why do you want that? Because if you have very few variables, then it is very easy. If I ask you, for instance, let's say that you have here, as you're analyzing some data. So you have some data here, you have a lot of individuals. You have individual 1, individual 2, individual 3. And all these are, for instance, for these individuals, you measure the age, gender, you measure glucose level, you measure many things, and then you measure something that will be, so all this is your X. And you measure whether this person has had a heart attack or not. So it will be 1, 0. And then you want y is a function of x. So which ones of these are more important to predict this one? So if all the thetas, so let's say that let's use thetas, so you are not confused. So if all the betas have, let's say, a linear model, x1, so x1 is age, and then u2 that is gender, and so on. If all the betas are different from zero, it's very difficult to say which ones variables are important. But now, if you promote explicitly sparsity, now it is very easy. If I ask you, okay, subject to this one, so the count of components of betas is smaller or equal to 1. So you would have to choose the variable that explains the best the variable you are trying to predict, or number of variables equal 2, or number of variables equal 3, or smaller or equal 3. So now it is very interpretable. And then this compressed sensing is something completely new for you, right? Then compressed sensing is another very nice idea. Let me see this one. So compressed sensing is this idea in which see nice picture of it. Somehow, this one. Maybe it is not nice picture. Okay, so some. How it is this one. So it is, let's say that you want to measure a function. Like I cannot find one. So let's say that I have a signal, function t. So this is x of t. You know the standard uniform sampling. So you take samples, and from x end you can recover x of t, right? This you know. Okay. And what if instead of taking regular samples, we take samples at random, completely at random? So this one here, this one here, this one here, this one here, completely at random. From the random samples, and they can gather. So from the random samples, can I recover x of t? And that is one that is compressed sensing. So in compressed sensing, these kind of sparsity constraints they also appear. So the function that you want to recover x of t has to be sparse in some space. And typically that space is the wavelet space or the Fourier transform space or some kind of space. It has to be sparse. Or feature selection, we have already said that. So feature selection is choosing which columns are relevant as predictors. And for reasons of memory, you have really a lot of data, maybe choosing a few active variables, say in some memory, the models. So the problem is that this L0 norm is not convex. It is discontinuous, and anything related to optimizing this has to follow a combinatorial approach. So an example of the table would be, okay, you only allow me to take two of these features. So I will take age and gender, or age and glucose, or gender and glucose. So at the end, I have to try all possible combinations. And all possible combinations, if the number of components is large, can be very expensive. So having L0 norm is complicated. Actually, because of the combinatorial nature of that problem, it is NP hard. So it is really, as the number of components grow, this one grows exponentially. So it is not feasible. So what you do is, okay, I will approximate the sparse problem by something else. And we have said that L1 tries to promote sparsity. So I cannot choose how many components you will be allowed to take, but naturally you will try to take few. So I cannot control how many, but you will take few. And then for solving this problem, L1 norm is convex. So convex, and now we know it is it gives rise to relatively easy methods and very good convergence. So all these proximal gradient methods we have studied, these two we have not. These are very much related to signal processing, coordinate descent, ADMM. So it promotes sparsity, but you cannot control the number of components that will be different from zero, and it still is computationally efficient. And the problem is that you may not find the sparsest solution, but probably it is sparse enough for your purposes. The other one is greedy methods. Okay, so greedy methods is really well understood here. So let's say that you allow me to choose only two variables here. So what I can do is, okay, I will solve it with one. So if I have to choose one variable only, which is the one that gives better predictions, let's say it is glucose. And then, because you allowed me for two, I will look for a second one. So I have chosen glucose, and now I look for something else. Okay? So that is a greedy approach in which you iteratively add variables that contribute the most, improving the objective. And you have here a couple of techniques. It's matching pursuit or orthogonal matching pursuit. And we will not see the details of these two, but they follow that idea. And the problem is that they are greedy. So greedy means that there are no global optimal guarantees. So the first step already conditions your trajectory in the variable space. But it is very fast, very easy to interpret. And then another approach to these sparsity problems can be these non-convex sparse penalties. Okay, so I will add a penalty term, but this penalty term will be non-convex, which is bad, but it will again try to promote the sparsity. In general, they will be based on these LP norms with P between 0 and 1. LP norms is a generalization of the L2, L1 norm. I think we will explain that at some point. So let's say that, let's see what is the L2 norm of a vector. This is the Euclidean norm. So it is, let me write it like this. Is the sum over I of all these components squared, and then you do the square root. Okay, what about the L1 norm? The L1 norm is the sum of all these, but now to the first power, and then you do, you don't do any root. So it is just kind of 1. So we can generalize to LP norm. So LP is sum this, the P power, then you do the P root. Okay, this is the LP norm. And P can take any value. So here P is equal 1, here P is equal 2, but you can say P equals 0.5, P equals 1.5, can be whatever. And for each one of them, you have a root. So actually the norms between 0 and 1, 0 is combinatorial, we already know. 0 is combinatorial, 1 is convex. And these LP norms between 0 and 1, they are not convex. They also promote sparsity. And yeah, that's it. So you may use this one, or you may use these ones, log sum penalties. These kind of functions, they are non-convex, and they tend to promote sparsity. And there are a couple of other techniques that are relatively niche techniques. So we will not see. If you're interested, you can explore them. But in general, it is, I will have a goal function I want to minimize, and I add some penalization to it. And this penalization will try to promote this sparsity, and maybe it's not as difficult to solve as the combinatorial problem that we had here at the beginning. So the true sparsity is combinatorial. So that is too hard if I have many variables, and maybe this one is not that hard. The other one is, okay, I will go combinatorial. So, you keep the sparsity constraint, and then you take some approach for that, mixing player programming, branch and bound, exhaustive search, if the problem is small, or some kind of genetic algorithms or whatever. But in general, they are much harder because you have to explore the combinatorial space. And here is another one that is, okay, I will solve a sequence of, I will solve a sequence of L1 norms. So this is the L1 norm, but it is weighted. And it is weighted by something that depends on the norm of xi. So, or the absolute value of xi. So let's say that for one component, one of the xi's in the current iteration, this xi is very small. It's 10 to the minus 6. So if it is 10, forget about the epsilon. So if it is 10 to the minus 6, the inverse of that is very high. So that means that if xi is small, then it will be very heavily penalized. And then in the next iteration, this minimizer will try to make xi equal 0 because it is much cheaper. And then now you have one 0 component, and then you keep iterating. Some other component, maybe again close to 0, you will try to make it 0. So this approach is called iterative reweighted method. It improves sparsity over the plane L1. Again, it is slower because you have to solve this problem multiple times. And it is approximate because the best would be, if you could afford, would be to solve the exact problem. But that is very expensive sometimes, and then you are happy with these approaches. Any questions? No? So we will leave it here for today.